All right, so we say that the boundary layer affects the drag on the aircraft, right? Moreover, we say that what we are concerned with regarding the boundary layer is primarily the friction drag it generates. Now, regarding friction drag, for different forms of boundary layers, we have laminar boundary layers and turbulent boundary layers. The friction drag produced by a laminar boundary layer is less than that of a turbulent boundary layer, similar to queuing in the subway. Crowding into the station. This analogy is provided to help everyone understand. Now, because the friction drag is significantly related to the boundary layer itself, we specifically want to take another look, aside from examining laminar and turbulent flows. What other factors can affect the friction drag of an aircraft? The first, of course, is the form of its boundary layer. The second is the surface area, which is easy to understand, right? The larger the area, the more places there are to be rubbed. Naturally, the larger the area, the greater the friction drag on the aircraft's surface. Additionally, when it comes to friction, we also have friction in solids, right? In our high school physics experiments, we also dealt with friction. So, what else affects solid friction? It is also affected by the surface roughness, isn't it? For fluids, the rougher the aircraft surface, the greater the friction drag. Therefore, for the friction of an aircraft in a fluid, there are mainly three influencing factors. One is the boundary layer, whether it is laminar or turbulent. The second is the surface area of the aircraft, and the third is the surface roughness. For our aircraft, if we want to maintain good performance, we need to minimize such frictional and stabilizing forces as much as possible. In discussing friction drag, we use the concept of the boundary layer. Here, I would like to remind students that the flow within the boundary layer involves friction. Is friction a relationship of energy conservation? Yes, it is a relationship of energy conservation. But no, it is not a relationship of mechanical energy conservation. Right? So, when we previously discussed the volatility theorem for interest rates, what kind of conservation did we use in our derivation? We used the conservation of mechanical energy, didn't we? Therefore, within the boundary layer, Bernoulli's principle is not applicable, right? Because mechanical energy is not conserved. Part of the energy is converted into thermal energy. Therefore, we cannot use the volatility theorem to explain the flow conditions within the boundary layer. Now, when it comes to aircraft flight, we want the aircraft to maintain a high-performance flight state, and we aim to reduce drag. What methods do we generally use to reduce the frictional drag of an aircraft? If we take a look at modern aircraft, we can notice that the surface of the aircraft is very smooth, right? There aren't many protrusions, and the steps and joints are kept as small as possible. The most important reason for this is that we want to reduce frictional drag. For the aircraft surface, we choose flush rivets, which do not protrude. This reduces the roughness of the aircraft surface. This is an important method we use in modern aircraft manufacturing processes to ensure reduced drag. Besides this, we have other ways to reduce the frictional drag of the aircraft. As we mentioned earlier, if the boundary layer transitions from laminar to turbulent flow, the frictional drag will be relatively large. Therefore, from the perspective of aircraft design, we try to use certain methods to maintain the laminar flow over a greater distance on the aircraft surface, keeping it laminar over a wider range. What methods are there? These include choosing laminar flow shapes, or what is called laminar surface design. The concept of laminar flow shapes was proposed quite early, while laminar surface design has been a subject of research in the past decade. It has been a significant research hotspot in the past decade. Additionally, we can use methods such as blowing or suction on the aircraft surface, including electromagnetic excitation and other techniques to try to maintain laminar flow. Let's take a brief look at this. What form does laminar flow shaping take? Let's watch an introductory short video about it. The globe turned to the environment, we can see that in the front part it shows the flow of people, and towards the back, do you see? The lines have dispersed, and this area has become a steady boundary layer flow. This is our rule. As the influence increases, we can observe that the area of the steady boundary layer expands. I take it back home. The opportunities grading the capable of remote concern. we see when the local type is at a negative angle of attack, the airflow on its upper surface mostly maintains a laminar flow. So, what kind of reasons can cause the laminar flow to transition to a steady flow? Well, what reasons can cause a transition? Mainly, it includes if the aircraft surface is not smooth. In this way, it will accelerate the transition from laminar flow to steady flow. Also, for example, some structural vibrations on the aircraft surface can also cause the laminar flow to transition to steady flow. And at the same time, the laminar flow transitions to flow. Another very important factor is the pressure gradient. Do we still remember what a pressure gradient is? We previously did some exercises on this, or you all have seen it, right? What is meant by an adverse pressure gradient refers to the region where the pressure increases in the direction of the flow from front to back. This is called an adverse pressure gradient. The transition from laminar to turbulent flow usually only occurs in the presence of an adverse pressure gradient. Therefore, when designing terrain, we need to find ways to reduce the adverse pressure gradient region and increase the favorable pressure gradient region.
Murder, almost Australian. We're getting a lift. We get a greater length of lambda 12 by modifying the trenches institution, who have changed in the airfoil shape.
The key to designing a laminar flow airfoil is to maintain a larger favorable pressure gradient under the same lift conditions.
Here is another Jonathan Gibbs. Are you saying that he has the same? The further adds of clothes that we did for a 20.
This is a type of laminar flow airfoil where the maximum thickness is positioned further back.
Thank you, everyone.
We can see that the most distinct difference from the previous airfoil is in the upper surface. Do we see it? Its laminar region and favorable pressure gradient region are longer. In the adverse pressure gradient area, the adverse pressure gradient is not that significant. Have you noticed? It's very flat on top, right? Then it gently slopes down, whereas the previous one shot up very high and then dropped down again. So in this way, it allows the boundary layer to maintain more of the attached region.
Again, with the increase in angle, the situation changes. Due to the geometry of the profile, the radius of the mean head is formed. The airflow at the leading edge must quickly speed up, creating an abrupt pressure minimum, strong adverse pressure gradient. The boundary layer remains in a laminar state for a longer distance than with the previous profile, but with the increase in angle, the transition point abruptly moves forward.
Now, at small angles of attack, it keeps laminar flow, but as the angle of attack increases, it becomes turbulent flow.
Thus, this produces the extent drag on the profile.
So, this is a design that facilitates laminar flow, which was one of the greatest aerodynamic discoveries during World War II. It was a research achievement by NASA, known by a different name at the time. Initially, it was believed to have a special and significant application, capable of greatly reducing aircraft drag. However, in practical engineering applications on aircraft, the effect was not as pronounced. Why is that? Because during World War II, the actual aircraft that were built did not have surface smoothness that could match the excellent smoothness of the wind tunnel models in the NACA wind tunnels. Therefore, the actual drag reduction effect when flying was not as good as imagined. However, this method had another effect. As the aircraft speed gradually increased and approached the speed of sound, this laminar flow airfoil produced less additional drag caused by shock waves. Therefore, later on, in high-speed aircraft, this type of laminar flow airfoil was widely used. However, as we have reached modern times, with advancements in aircraft manufacturing technology. The aircraft surface can be made smoother, allowing for more use of this laminar flow design, like style. However, during the actual flight of the aircraft, as we mentioned earlier, the roughness of the aircraft surface, such as protrusions and features, can cause the laminar flow to transition into turbulent flow. Therefore, a well-designed laminar flow aircraft, once it operates under harsh conditions, such as when there is this rainfall, or a lot of dust and dirt accumulating on the machine, it will also significantly increase the frictional drag of the aircraft. This is currently a troublesome point in our study of laminar flow, as it is quite challenging to keep the aircraft surface in a very smooth state during flight and actual use. This is relatively more difficult. So, what we are discussing here is frictional drag, and we are reviewing the essence of how frictional drag is generated. It is due to the interaction between layers within the boundary layer. Right? The shear between layers causes this part of the drag. The next type of drag is also caused by the boundary layer, but this drag is different from the previous shear. This main drag, we call it pressure drag. Let's take a look at how it comes about. For a steady flow, when it hits the front of an object, there should be a stagnation point at the very front, right? This is the point where the velocity is zero. On both sides of the stagnation point, the airflow accelerates, and then after accelerating, it goes through a deceleration process. Theoretically, it will, at the position closest to the trailing edge, a so-called rear stagnation point is formed, where the velocity is zero. After this, the flow leaves the surface of the object and accelerates again, eventually returning to the free stream velocity far upstream. Considering the process from front to back, it involves decelerating to zero, then accelerating, and here again, decelerating to zero, and accelerating. Therefore, what is the pressure like in the areas where deceleration occurs? It's large, right? Where is the acceleration area? The pressure is low, and because there is a deceleration process both in front and behind, the pressure difference between the front and back is the same. So this airfoil, in our case, under no wind conditions, there will be no pressure difference between the front and back. It won't generate drag caused by pressure difference. But in reality, it's different. Earlier, we saw many videos, and as the angle of attack increases, in fact, the airflow over the wing surface cannot always remain attached and flow along the surface. After a certain distance, due to the effect of friction, as we mentioned earlier, there's a principle of mechanical energy non-conservation, right? Pressure energy and kinetic energy cannot be completely converted into each other. Therefore, as mechanical energy is gradually lost due to friction, after reaching a certain point, pressure energy can no longer be fully converted into kinetic energy. So what happens then? The flow can no longer adhere to the surface of the machine. As a result, separation occurs, and it detaches. So what happens after separation? In fact, it maintains a relatively low pressure state as it moves downstream. At this point, we say that due to the previous stagnation point, which still exists, this high pressure area still exists, but the high pressure area behind disappears. What happens between the front and back? The pressure is higher at the front. The pressure is lower at the back, creating a pressure difference between the front and back. Right? This pressure difference results in a significant drag, which we call pressure drag. This occurs because the flow of the boundary layer causes mechanical energy not to be conserved, leading to flow. After reaching a certain point, it separates from the surface, creating a pressure difference between the front and back, thus resulting in this pressure drag. Let's take a look at the characteristics of boundary layer separation. Depending on the form of the boundary layer, we will examine both the laminar boundary layer and the turbulent boundary layer. What is your relationship with him? In the same expanding duct, part of the flow, we slightly add a rough object to the surface, causing the laminar boundary layer to transform into a turbulent boundary layer. Above, it remains a laminar boundary layer at least, as we can observe. The turbulent boundary layer, notice it doesn't separate, right? Because you can see that there is still flow attached to the edge. Correct. However, the laminar boundary layer is very orderly, but separates from the boundary quite early. doesn't it? This results in airflow separation. So, from the perspective of boundary separation, there is a significant difference between laminar and turbulent flows, as the laminar boundary layer easily separates under an adverse pressure gradient. The laminar flow separates, whereas the turbulent boundary layer, due to the presence of many vortices within it, allows these vortices to bring higher speeds from the outer flow into the boundary layer. This continuously replenishes the boundary layer with kinetic energy, causing separation to occur much later. This is a significant difference between turbulent and laminar boundary layers from the perspective of boundary layer separation. So, what important insights does this provide for our aerodynamics and drag reduction design? In fact, when an object moves through the air, if separation occurs, the pressure drag caused by separation is much greater than the friction drag. Therefore, if an object experiences separation and we want to reduce drag, the primary issue we need to address is usually the separation problem. For example, as we've mentioned with a golf ball, when it moves through the air, separation occurs in its wake. From the perspective of reducing drag on a golf ball, since it experiences separation, the main issue is the pressure drag caused by separation. Therefore, we need to find ways to delay this separation. According to the concepts we mentioned earlier, is it easier for laminar flow layers to separate or for steady flow layers to separate? Laminar flow tends to separate easily, right? Therefore, from the perspective of addressing the main contradiction, we should first transform this laminar flow into a turbulent boundary layer so that it can separate later. So what do? We notice that the surface of a golf ball is dimpled, right? The purpose of these dimples is to transform the boundary layer into a turbulent boundary layer, which allows for a smaller separation region, thereby reducing the pressure drag. This mainly corresponds to, for low-speed flying objects, we usually adopt drag reduction measures, whereas for high-speed flying objects. In the design process, we have already minimized its separation to the greatest extent. Why? Because high-speed objects typically do not use such spherical cross-sections, nor would they produce this kind of hemispherical or square cross-section. We shape them into a teardrop cross-section. Why the cross-section? It's to reduce separation. This shape of object has the weakest separation, thus the drag it causes, this pressure drag, is the smallest. At the same time, as the speed of the object's movement continuously increases, it corresponds to the concept we mentioned earlier, which is the concept of the Reynolds number. As the Reynolds number continuously increases, in fact, for high-speed moving objects, the boundary layer maintains non-separation more strongly. Therefore, for high-speed moving objects, we have actually already achieved a shape with a high Reynolds number and streamlined design, which significantly reduces pressure drag. For high-speed objects, the first thing we address is this issue. When the primary issue is no longer pressure drag, we should then focus on reducing the secondary issue, elevating it to the primary concern, which is the high friction drag. Therefore, for high-speed moving objects, we adopt a laminar boundary layer design. However, there are exceptions to everything. For example, in the case of large military transport aircraft, the rear needs to have a ramp. On one hand, this is to facilitate loading, and on the other hand, to make airdrops easier. This area will become a large expansion flow, a significant adverse pressure gradient zone. When the adverse pressure gradient is too strong, it can easily cause flow separation. So what do we do in this situation? We usually add a small device here. What is this device for? In fact, it is a vortex generator, which actively stirs the airflow to create vortices. As we mentioned earlier, a stable boundary layer cannot bring the kinetic energy of the external flow close to the surface of the aircraft through vortices. Using vortex generators can also produce a similar effect. In this way, it allows the rear part of the aircraft to maintain more contact with the surface flow, thereby reducing its pressure drag. This is a very special area, and as in most places, there won't actually be such large separation regions. Here, we are highlighting the main issue of drag reduction for different objects. For different low-speed objects, which are non-streamlined, what is the main type of drag they face? It's pressure drag, right? However, for streamlined objects and high-speed moving objects, since they basically no longer have separation and pressure drag, the main issue for drag reduction becomes friction drag. All right, what we discussed above is the theoretical aspect of friction drag and pressure drag. Now, let's translate this into practical application. Let's observe how the drag of an airfoil changes with the angle of attack. Using the same Nike 2412E model, we see that when the angle of attack is relatively small, how does the drag coefficient behave? It's relatively small and basically remains unchanged, right? Why is that? Because when the angles are relatively small, the pressure gradient is not very strong. The separation of airflow is not significant, so where does the drag come from at this time? The separation of airflow is not significant, so our drag comes from friction, frictional drag. Let's think about our factors. The three factors that affect frictional drag. The first is laminar or steady flow, right? The second is area, and the third is surface roughness, correct? Within the range of response angles, these three factors have basically not changed. Therefore, the frictional drag maintains an approximately unchanged characteristic. Because it is mainly frictional drag, the drag remains unchanged. However, as the angle of attack increases, we say that with the increase in the angle of attack, the upper surface of the wing increases, and the suction wind on the upper surface of the wing strengthens, right? So, the suction wind strengthens and takes on this form. From the perspective of up and down, the suction increases. And from the perspective of front and back, what gradient increases? The pressure gradient increases, right? Due to the strong adverse pressure gradient, it causes the airflow to separate. Once separation occurs, what kind of drag appears? Pressure drag appears. Therefore, as the angle of attack increases, the drag increases rapidly. At this point, the drag includes both frictional drag and pressure drag components. This drag should exhibit a nonlinear increase. So, for a two-dimensional type, what does its drag consist of? It consists of two components, right? Frictional drag and pressure drag. Therefore, we refer to the sum of frictional drag and pressure drag as form drag or profile drag. Correspondingly, this refers to the cross-section. So this is a concept that I hope everyone can understand. All right, now please think about this question. What is the definition of the transition point? It refers to. Lift is this. Due to changes in the angle of attack causing changes in lift. B, it is. The relative speed decreases because of such a point at zero. C is the point where the boundary layer transitions from laminar to turbulent flow. D, it is the E-type angle of attack increase, beyond which the terrain will stall. What is the definition of the transition point? Please answer. Time's up. Regarding the concept, our classmates' understanding is quite good. What should we choose for this question? It should be C, right? All right, earlier we talked about resistance. Next, let's talk about the characteristics of example sentences as soon as we talk. So, quote, as soon as we talk. Example sentences. Example sentences should have a reference point, right? We say it's based on which reference point we take the example sentence. So for a two-dimensional type, where is its example sentence reference point? Yes, we take it at 25% of the relative chord length, which is a point obtained by multiplying 25% by the chord length from the leading edge of the airfoil. We will take the example sentence at this point. Now, let's observe for an airfoil like the Nike 2412. As the angle of attack changes, this gray line represents the change in the lift coefficient. We have already mentioned this earlier. And the blue line represents the change in the example sentence coefficient. Here we can see that, in the case of small to medium angles of attack, if we take the example sentence at the 25% point, what characteristic do we observe? As the angle of attack increases, the example sentence remains basically unchanged, right? So, this is the most basic characteristic of our line of example sentences. That is, in the case of small to medium angles around the 25% chord, its example sentence remains unchanged. Therefore, we have another term for this example, sentence coefficient, which we call zero lift. The example sentence coefficient is represented by CF, 0. Why? Because when the lift is 0, the example sentence is it. And what about when the lift increases? The example sentence is still it, so we call it the zero lift sentence. Then some of our students might ask, if the lift is 0, why is there still an example sentence? How do we explain this issue? Is it possible for B to be 0, but the example sentence is not 0? Is there such a possibility? Can you imagine it? At this point, the resultant force corresponds to this. Is it 0 if these two forces are equal in magnitude and opposite in direction? It is 0, right? Is the example sentence 0 at this point? So, as long as there is a pair of force couples, what is called a force couple is when they are equal in magnitude and opposite in direction. With such a pair, as long as there is a pair of forces, isn't there only an example sentence without force? Right. So, why is there a moment when the lift of the airplane is 0? It's because of the existence of such a force couple, or rather countless pairs of force couples, that this moment is created. All right, now let's look at what happens as the angle of attack increases. Generally speaking, an example usually has an upward tilt, characterized by a change towards positive values. As we mentioned earlier, the positive direction of the moment is defined as nose up being positive and nose down being negative. In other words, as the angle of attack increases, there is a nose up trend. Why is that? Because for most airfoils, airflow separation starts from the trailing edge. For an airfoil, there is lift from front to back, right? But as the angle of attack increases, due to airflow separation, the lift at the rear part disappears. From the perspective of life manifestation, we can see that it's not linear anymore. This part starts to drop down, and it means that this part of the lift has disappeared. We say that before this part of the lift disappears, it still contributes to the nose up or nose down rate for the front. The rear part is raised, and the front position is the nose attitude, right? Due to the increase in the angle of attack, this part of the nose down force disappears. So, doesn't it reflect the overall force characteristic by lifting up? Right. This is a very important reason why an increase in the angle of attack causes the aircraft to exhibit a nose-up attitude, which is due to the separation of airflow at the rear. All right, here we need to introduce a very important concept, a definition called the focus and aerodynamic center. What are the focus and aerodynamic center? They refer to the point where, as the angle of attack increases, the moment arm remains unchanged. We call this point the focus, or aerodynamic center. Now, if we correspond this to a two-dimensional operation, then where should the focus or aerodynamic center be under small to medium angles of attack in two-dimensional operation? Pressure. Definition. As the angle of attack changes, the moment remains unchanged. So, let's take a look. Speaking from the example sentence curve, does the example sentence curve change? It doesn't change under the guidance of small and medium, right? At which point do we take the example sentence curve? The example sentence. Good. Afternoon, everyone. The example sentence is taken at the point of 25% chord length, right? So for a 20 billion type, where should its focus be on the small and medium angles? Where should it be? It should correspond to the position at 25% chord length, right? So, when the angle of attack is relatively small, since the example sentence at this 25% point doesn't change, it means that at this point, under the guidance of the middle class, its focus is located at such a position. From this, we can further understand what is another way to interpret this focus. We say that if for an object, for example, corresponding to a point on the object, and then we take a reference point, this is the reference point. Then if the force applied on this object continues to increase, then where is the point of application of this force such that, regardless of whether it increases or decreases, its moment remains unchanged? It is at this height. Is it if and only if the point of application of the force? When the point is at this point, no matter how it changes, its magnitude remains unchanged, right? So, for the focal point, we have another way of understanding it, which is that the focal point can be understood as called the point of application of the lift increment. Why is that? Because whether the lift increases or decreases, the moment corresponding to this point remains completely unchanged, right? Now, we need to clarify two key concepts for everyone. We previously mentioned two very important points. We just talked a lot about this, called the focal point. And we also mentioned another point before, called the center of pressure. What is the difference between these 2 points? The focal point is the point where the moment remains unchanged, right? Under normal conditions, it is the point at 25% of the chord length, so the moment is unchanged. But the moment is not necessarily zero, right? What does the center of pressure refer to? The center of pressure refers to the point of application of the aerodynamic resultant force. How should the moment be? The moment is zero at such a point, right? We need to distinguish between these two concepts. Later on, especially in pilot exams, this concept is tested quite frequently. In your future licensing exams, we will discuss it in more detail later. All right, regarding drag and lift, that's all we have to say. Next, let's go over the geometric parameters of type E from the previous lecture, and the lift and drag information from this lecture to integrate them. Let's see how different parameters affect the aircraft's dynamics. First, we compare 3 operations. This includes the NACI 0010. What common points do the 2410 and 4410 of type E have? From front to back, their thickness remains constant, while what changes is their camber. From 2% to 0% to 2% and then to 4%. Now, let's take a look at how the drag, lift, drag, and moment curves change as the angle of attack increases. First, let's look at the lift characteristics. How are these 3 lines? They are basically parallel, right? Then, as the camber increases, meaning the more it curves downward, what do we find? How is the lift coefficient at the same angle of attack? It increases, right? Or we could also say that the stall angle decreases, right? So, this is one way to understand it. Additionally, this, yes. Regarding this, we can remember it using this understanding for now. So, if the camber increases, the main effect is that the stall angle decreases, and then it affects the lift coefficient at the angle of attack. increases. Meanwhile, since this line is parallel, we find how the lift line slope behaves. With the change in camber, it actually remains unchanged, right? Then let's take a look at the drag characteristics. We focus on the small to medium impact because when our aircraft is flying, the focus is mainly within the small to medium angle of attack range. What do we find? The green line represents the largest camber, the blue is the intermediate, and the red is the smallest camber. So, how about it? As the camber increases, the drag becomes greater, right? We can understand it this way. When the camber is 0, its surface area is actually the smallest. As the camber increases, its surface area begins to increase. Therefore, its friction drag, mainly under small to medium angles, is primarily friction drag, isn't it? The friction drag is a process of gradual increase, and this is the drag characteristic. Now, let's take a look at the moment characteristics. So, what about the moment characteristics? As the camber increases, it is reflected as. Should we increase towards the direction of the morning, towards the entrance, or towards exit D? Is it a political change or a change in protection? The first point is that it becomes negative, right? The red type, it is a symmetrical type, correct? A symmetrical type. So, when the angle of attack is 0, the forces above and below should be symmetrical, right? Therefore, it definitely won't generate a moment. So the 0 point is 0. The state is 0. Moreover, we mentioned that for retrograde motion, on medium and small scales, its focal point is at the 25% extension, right? If we take this point as an example with changes in the angle of attack, this example should remain unchanged. So it proceeds symmetrically. How about it? As the angle of attack increases, its example remains unchanged, right? And as the camber increases, we can see that the greater the camber, the larger the nose-down moment becomes. Moreover, with the increase in the angle of attack, under the influence of growth, its rate remains unchanged. So, once we have this basic understanding, what particularly troublesome issue should we analyze next? How should the center of pressure change? To be honest with everyone, in actual aircraft design, for those of us in the aircraft design field, we basically don't consider how the center of pressure changes back and forth with the change in the line of pressure. This type of question only appears in pilot exams, and I don't know why they ask such questions, but it's particularly boring, yet they always include such questions. So let's discuss it here. We already know that the example of the bell sound remains unchanged, right? It doesn't change as the influence increases. So we want to ask everyone, first of all, for a symmetric type. As the angle of attack increases, how will the center of pressure change? Does it change? Well, we say that the center of pressure corresponds to the example sentence, whether that point changes or remains constant at 0. It's the point that remains constant at 0, right? So, for a symmetric type, as the angle of attack increases, for the focus and the 25% core point, if you take the example sentence, it also remains constant at 0, right? So, for a symmetric type, where should its center of pressure be? It's this 25% chord length position, right? Alright, this is relatively easy to understand. Then, we move on to something a bit more complicated, which is the operation with positive camber. For an operation with positive camber, how should the center of pressure change as the angle of attack increases? How do we consider this issue? Let's first look at the 25% chord length position. So, from the diagram, we know we have an important concept. What is it? For the focus, its focal point is constant, right? For small angles, the example remains unchanged, correct? So, how does the lift change as the angle of attack increases? The lift increases, doesn't it? As the angle of attack increases, the lift increases, but the moment remains unchanged. What does this indicate? Doesn't it indicate that the point of action has changed, right? Only when the point of action changes can the force increase while the magnitude remains the same. All right, let me ask everyone. As the angle of attack increases, the lift increases, correct? The lift increases, but the moment remains unchanged. We say the moment equals force multiplied by distance, right? The force increases, but the total moment remains unchanged. What does this say about the lever arm? The lever arm decreases, doesn't it? So, as the influence increases, the lever arm definitely decreases. At the same time, let's discuss where the point of action of this force is located. Is it before or after the focal point? Should the center of pressure be before or after the focal point? For a positive camber operation, should its center of pressure be before or after the focal point? What kind of point is a reasonable point of action, right? Alright, should the point of action of the resultant force be before or after the intersection point? Is our example direction nose up or nose down? Positive or negative? Negative is nose up, head up, nose down. Nose down. So, what kind of place would generate a nose down moment? It's at the back, right? So, for a positive camber in reverse, actually, its center of pressure within the positive angle of attack range is at the back, isn't it? And as the angle of attack increases, how should the position of the center of pressure change? The moment arm will become smaller, right? So it will move closer to the focal point, moving forward. All right, this is the method to analyze this rather tricky problem. You all understand the logic, right? For those not specializing, just know its example. Stays unchanged. All right, now let's talk about how changes in thickness affect maneuverability. So let's take a look. As the angle of attack increases, is there any change in the first half? No change. It mainly manifests in the latter part. Why is that? It's mainly because as the thickness increases, the leading edge radius increases. Yeah. After the leading edge radius increases, it actually delays the onset of separation. Therefore, its stall angle of attack will increase, and at the same time, the maximum lift coefficient will increase. This is the impact of increased thickness on lift. However, the lift curve slope and the zero lift angle of attack remain completely unchanged, right? Let's talk about drag. We can see that the green line represents the greatest thickness, and the red line represents the smallest thickness. The drag increases, which is also easy to understand, right? Due to the increase in thickness, what happens to its surface area? It increases, doesn't it? Compared to when the camber was increased earlier, this is even more noticeable. Therefore, as the thickness increases, its drag will rapidly increase at medium and small angles of attack, while at large angles of attack, we see the trend is exactly the opposite. Why is that? When at large angles of attack, where does the drag come from? What is the main increase? Pressure drag, right? We mentioned earlier that as the thickness increases, the separation becomes weaker and occurs later, correct? Therefore, the rate of increase in pressure drag will be relatively small. So with greater thickness, at slightly larger angles, the drag will actually be lower. Now, looking at the example sentence, since the lift hasn't changed, the moment hasn't changed either, right? So why did this change occur in the latter part? It's actually directly related to separation, isn't it? We said that the reason for the upward tilt in this example is mainly because separation begins to occur at the trailing edge. Due to the increased thickness, the separation changes. So what does that mean for the type? With a relatively reduced rear, its warping will occur to a lesser extent, okay? Then let's take another look at the Reynolds number. As we mentioned earlier, the Reynolds number reflects the comparison between inertial and viscous forces. The larger the Reynolds number, what does it indicate? The greater the inertial force, right? The faster the plane flies, the larger the application area. Now let's take a look. Under different Reynolds numbers, including 100,000, 350,000, and 600,000, we can observe how the corresponding critical angle of attack changes as the Reynolds number increases. Higher, right? Because the larger the Reynolds number, the later the flow separation occurs, which means the maximum lift coefficient will be greater. At the same time, with a larger Reynolds number, it can better maintain laminar flow, right? So for high-speed objects with a high Reynolds number, E, it is easier to maintain laminar flow. At this point, we can see that when the Reynolds number is large, the friction drag coefficient is relatively the smallest. In terms of examples, the three are basically similar. So, this is the impact of an increase in the Reynolds number on drag and primarily on lift. After discussing the liaison point, let's talk about the liaison point again. Then we'll discuss one of the most important things, which is the impact of trailing edge deflection on lift, drag, and moment. Why is this considered the most important? Because all the knowledge we will cover later about aircraft stability and control is closely related to it. So, students, please pay special attention as we compare different scenarios of trailing edge segments. The baseline scenario is this symmetric airfoil in green, with no deflection in blue, and red representing downward deflections of 5 and 10 degrees, respectively. Then, the pink and the ochre below represent upward deflections of 5 and 10 degrees, respectively. Regarding the impact of these degree deflections, we can understand it as a change in camber. Now, if we understand it as a change in camber, let's analyze these curves. So in summer, can we understand it as a decrease or an increase in camber? An increase, right? It curves downward, correct? Therefore, when the camber increases, how does it reflect on the lift coefficient under the same angle of attack? It increases, doesn't it? So therefore, the trailing edge's camber increases in summer, so the lift coefficient will increase. This is the first way to understand it. Additionally, from the pilot's perspective, what is the second way to understand it? As it deflects downward, the trailing edge actually curves further down, right? If we consider this as creating an equivalent front line connecting the leading and trailing edges, what happens in summer? The chord line rises, doesn't it? This results in an increased effective angle of attack. Increased, so it is believed that the lift coefficient increases, which is also a way of understanding it. Both are valid. In summary, as summer increases, from a lower angle of attack, the lift system increases. Conversely, in winter, the camber decreases, and the lift coefficient decreases. This is the impact of the trailing edge deflecting up and down on the lift coefficient at the same angle of attack, which is the first concept we want everyone to understand. The second, let's focus on the impact of stalling. What did we find out? We said, going up will lead to an earlier stall angle of attack, right? In our previous section, we made a mistake, and in the next section, our original intention was to increase the lift coefficient, wasn't it? But if we consider extreme conditions, when the angle of attack is very large, going up in summer will actually cause a stall to occur earlier, and a stall will happen under a smaller influence. This is significant for our control. It has a very important impact. We hope to first understand this concept here, and later when we discuss stability and control, we will analyze its significance. Then regarding the structure, we are not very concerned, because our control does not mainly rely on the structure. Sometimes we rely on examples. Let's look at symmetry. The example is 0, right? The example is 0, right? Then with summer, what does the example become? It becomes a downward example, right? Then with the previous section, it becomes an upward example. This is the influence of the rudder on the example. So what is the use of this? The control surfaces of our aircraft, most of our control surfaces rely on lift or torque for control. In fact, they are all elevators, all rear control. A rudder deflecting up and down is also a rear control surface. And ailerons deflecting up and down are also control surfaces. We use this method to control the aircraft, so students should focus on remembering what kind of impact the deflection of the control surfaces has. Let's review what we just discussed about the changes in airfoil shape and their impact on the lift and drag characteristics. First, we talked about the influence of camber. In fact, regarding camber, no matter how the camber changes, the lift curve slope actually remains unchanged. This value, if we tell you, is 2 pi per radian, which is very important for aircraft design. However, for pilots, it's enough to know that the lift curve slope is the same. Meanwhile, what does an increase in camber change? If the lift curve slope doesn't change, what does change? It's the stall angle, right? Or rather, it's the lift coefficient at the same angle of attack. So, when camber increases, the stall angle should decrease, and the lift coefficient at the same angle of attack should increase. Corresponding to the example sentence, it should be a nose down. We must remember this example sentence. Then, for a symmetric airfoil, which is a special case of zero camber operation, it's stalled. Example sentence. Should not always be zero, right? Because we say that the zero lift line does not change with the angle of attack. So for a symmetric airfoil, it is the same on both sides.